Hi everyone, and welcome to this video. This is part of a 3 video series on linear regression, and we're going to discuss the basic concept of linear regression and later build up and implement the concepts in R and Python in the later series of this video. So linear regression is a supervised learning technique, machine learning technique, and the aim is just building a mathematical model that describes the relationship among variables. And here we'll be building the relationship between a dependent variable, which is our response, and also independent variable or variables, which are now our regressors or the explanatory variable. It's important to note that in linear regression, our response, now the target variable, the y variable, is continuous in nature. And this, for example, it's like the amount of cells, the amount of rainfall, the number of the exam scores against the hours studied, or even other factors such as the amount of blood sugar in the body. So as long as your variable is continuous, linear regression is a model that you can build to explain the variables, the relationship among the variables. So as just mentioned, we are just trying to fit a mathematical function of y being a function of x, and it's important to know that there may not be a perfect relationship, like a perfectly linear relationship. And here I just have an example here where we are having a scatter plot between year-end evaluation and mid-year evaluation. Our goal is in linear regression, just try to find a line that fits upon as many points as possible. So here we had performance evaluation of 10 employees obtained at mid-year, and the goal is just to compare it with end-year evaluation so that can mid-year be a good predictor of end-year evaluation. So this is the line. When we try to fit the line, we see that we just try to be as close as possible to many points and minimize the distance between a point and the line. Now the mathematical model that we'll be using, it's this equation where we are saying yi equals to beta naught plus beta 1 xi plus error terms. And for us, we remember that this is one of the equations that we encountered from mathematics, where I used to say equation of a straight line, where we said y equals to mx plus c. And when we have many variables of x, we just expand the equation just to fit each x, like x1, x2 until xn with the respective beta. So we have this error term, and this error term is now the variable component of the equation, because remember, the x are observations. You will have made x observations and the y observation, of course. So meaning the only thing that is varying is the error terms. So the error terms are the ones which are varying in this equation, while the x are fixed in this component. So the most important parameters that we'll be requiring so that we build our model is beta naught and beta 1, and I will see how we compute them. And then of course xi is the predictors, now the independent variables, while ei is the random terms, and these random terms we are assuming that they follow a standard normal distribution, meaning that the mean is 0 and the variance is 1, and this builds up to the assumptions that we are making in the model. Another assumption that we'll be making is about independence of observations. So observation at point 1 and observation of point 2. So x1 meaning observation 1, observation 2, observation 3, all of them are independent. This implies that the error terms at point 1 and point 2, for example, ei and ej, are uncorrelated, implying that there is no relationship, or there is no correlation between ei and ej, and therefore since there is no correlation, the covariance among them is 0. So just as I've mentioned, those are the assumptions. We also have another assumption where we are calling upon the constants of variance. So this means that the variation, we said that we want our variance is 1. So our variance among the observations should be constant. And this is something that we'll be evaluating at the end of building the model. Another thing, as you will be building now multiple variables, it's important to know that there should not be multicollinearity among the variables. So what does this mean? If you're having x1, x2, and maybe x3, and x1, x2, x3 are correlated, meaning that each of them can equally explain y. So this means that you're adding complexity to your model, rather than if one variable can explain y very well, why add all of this? and make complexity in your model. A good example is when you're having height, weight, and also BMI. Remember, BMI is computed from height and weight. And when we do this, when we add each of these to the model, yet we are trying to predict something like blood sugar level, yet we have height, weight, and also BMI, we are adding more complexity because BMI is computed from height and weight and therefore correlated to height and weight. Therefore, this will make your model perform poorly at the end. There are many ways in which you can measure multicollinearity. We'll talk about them when implementing the example in R. So how do we fit linear regression? One approach that we use is the least squares approach. We have other approaches such as the maximum likelihood approach, but here we use a concept of linear least squares approach. This is one of the approaches that we use, and it's the most common one. And in least square approach, remember we had these error terms. The error terms in just simpler explanation is between the observed and the predicted. You have a yi which is predicted, but you will have a yi that is expected based on the calculation, the one that you'll be estimating based on the equation that you have. So you want the difference between the actual and the real to be as minimum as possible. So through least squares approach, we'll be estimating the parameters of beta naught and beta 1 that minimizes the error sum of squares. So here, remember, yi is the observed, then yi at is the estimator. Whenever we have at in an equation, we are showcasing estimators. So we want the difference between the actual equation and the estimated value of y to be as minimum as possible so that our model can be a depiction of the real life. So just as I've mentioned, beta naught minus beta 1 xi, this part is the estimated part. So in order to solve this equation that we have here, the approach is to employ calculus, where we'll be doing a partial derivative with respect to each parameter. So we do a partial derivative of this equation based with respect to beta naught, then set the solution to 0 so that you can find the value of beta naught. Also then repeat the same procedure, but now partial derivative with respect to beta 1, and then set the solution to 0 so that you can obtain the values. So when we do the partial derivative with respect to beta naught, what we find that beta naught is computed by y bar minus beta 1 x bar, and y bar is the mean of y and x bar is the mean of x. So how do we compute this? I've added some resources to the video description, but you can add to the comment if you may want me to go into the detail of how we derive this. But this is what we have, and when we go to fitting the model in R and Python, this calculations is done and fitted using the model functions that we'll be using. Also, for beta 1 is a little bit longer, but once you solve this equation, the derivative of the equation with respect to beta 1, we find out that beta 1 is computed as the sum of the product of xi minus x bar with yi minus y bar divided by the square of xi minus x bar squared, now the sum of it. So this is how, in order to get the values of beta naught and beta 1, you require these formulas, and it will help you now compute the least squares estimators for beta naught and beta 1. Here we have an example, and in this example we had observation of x and y, so 10 series of x and y observations, and what we did here, we just wanted to get now the values of each. So we have the totals at the bottom, and then what you compute is now, of course, remember from our formulas of beta naught and beta 1, what we saw is that we need y bar and x bar, and that's just the mean. X bar is the mean, so the mean of all of this and the mean of this. So this is just a snippet from a spreadsheet, Excel spreadsheet. Then we need the difference between the actual observation and the mean, so x minus x bar. So when we say 3.86 minus 4.4, we get that one, negative 0.6. You have all of them, then get the sum at the bottom. Then also take the square of this now, x minus x bar squared. Remember, we need it as the denominator of computing beta 1. You have all of them here and get the sum at the bottom. We also need yi minus y bar. See, we have it in this formula. So y minus the mean of y. Get it here and compute all of them and have the sum at the bottom. Then lastly, you need the product between x minus x bar, also x minus x bar, and y minus y bar. So when you say negative 0.6214 multiplied by negative 0.9829, you get the solution there. Then add all of them at the bottom. Come and add all of them at the bottom. What you'll have is 2.54209 as the solution for beta naught and 0.77529 as the solution of beta 1. And you add it to the equation, and that's what you have. So I've mentioned about when we'll be building the model, there are things we need to evaluate just to see how well is our model performing. And some of the metrics we use when we are handling linear regression, one of them is the R-squared. And R-squared is just, we want to see the proportion of variance in the dependent variable explained by the model. So let's say in this equation, and we were able to build maybe several models. We have this one equation, maybe another equation, and another equation. We want to see which equations explains as much as variation in the y. Which equation explains much variation in the y as possible. So that's what we use the R-squared. These are computed automatically by the software, so you need not to understand the formula going behind it. But we also have now an adjusted R-squared, which just takes into account the number of variables you've added. Remember when we mentioned about things like multicollinearity, and of course the more variables you add, the more complexity you add to your model. So if there are variables you've added and they are not speaking as much as possible, then they're not speaking to the model in any way better. Then that means that they're adding complexity and they're just becoming irrelevant variables. So adjusted R-square will adjust for that, for the number of predictors. We also have mean squared error, which is just the differences of the square between the observed and the predicted. Remember we said yi minus yi at. And then if you get the square root, it's just the square root of this mean. You can also have an absolute. And then another function that we have that is not most commonly used in linear regression, however, it's used in terms like it's mostly used in time series. We have the archaic information criterion and the Bayesian information criterion. And this is just penalizing the model complexity and assess the trade-off between model fit and simplicity. So it just looks at how best the model is fitting and its simplicity. So if you have more complexity, it kind of penalizes you more. And we always want to strive to get models with lower values of AIC and BIC. Another statistic we can use is the F statistic, and this is just the overall significance of the regression model. So how is this model significant at the end of it all? At maybe 5% significance level. Finally, we can also use some diagnostic plots just to see how best our model is doing and check for assumptions. And one of them, we can check for the assumption of equality of variance using the residuals versus fitted plots. These plots are mostly really well to design when in R, because they are well embedded in the functionality of R. So this is what we have. One of them is the residual versus fitted, and I've just mentioned it's about the equality of variance. We also have the normal QQ plot, and this is just looking at how our residuals, now the residuals, are they following a normal distribution, and we'll see how they look. The last two also look a little bit on the about the variance. They're not most commonly used, but I'll speak a little bit on the last one, residual versus the leverage plot, and this helps us to look at the outliers. And we had not mentioned it in the assumptions, but linear regression does not perform well when your data has outliers. And at this point, you'll be able to see, are you having many outliers, and maybe perform further analysis just to check how they affect your model and so forth. So there we have it. We've been able to discuss about the concept of linear regression. We've mentioned that it's a supervised learning approach, and we are trying to fit a relationship between y and x, and in our instance, y is a continuous variable. We use linear regression in several applications, such as prediction of sales, prediction of exam scores, prediction of rainfall, as long as the y variable is continuous in nature. We've also mentioned about the assumption of linear regression, and we use the simple Nemonikov line, where it's linearity, independence, normality of the residuals, and the equality of variance. We've also seen how we are able to compute the estimators of beta naught and beta 1. using the least squares approach, and talked about some metrics to evaluate the model, such as the adjusted R squared, the F statistics, and the root mean squared error. So there we have it. I hope this video has been educative as possible, and I'll see you in the next series where we'll be implementing this concept in R.